Hi, this is my video number 33. I'll talk on tauberian and abelian theorem. Yeah. Abelian and tauberian and abelian theorem. So, if you consider a function ft as that, and if we find the the Laplace transform of ft, Laplace transform of f. So you have this is from the definition of Laplace transform. This is our fx ft. K factorial dt, and I think I'm missing a k here, should be okay. So if you do this, of course the summation you can bring it out, then it's become that you have ak, you can put ak there, e minus st tk to k factorial dt. In fact, k factorial you can bring it out, this k equal to 0 to n. Then you can integrate that by parts couple of times, so you will end up all this thing as that k is 0 to n ak s minus n minus k minus 1. So it's not difficult, that you just do the integration by parts, and then you can come up with that. So if you look at this, if you write in the normal form, you can write this as when k naught, you have a naught s a naught over s plus a1 over s2 and so on. Alright, plus an over s n plus 1. Okay, so obviously from there you can multiply by s, so you can have fs is equal to a naught plus a1 over s and so on, an over sn. So if you take a limit, s goes to infinity, so what you can see, if you take a limit s goes to infinity, s of fs, so what you have, this is all zeros, so what you have, this is just a naught. So the same thing, if you take limit ss goes to infinity, s n plus 1 fs, this is just equal to limit your function, our function, this is our function here, approaches t from positive, f of n t, right? So this is equal to an. It is not difficult to see those things. So that's what we can say, is that the behavior of the function near t0, from positive, is reflected in the behavior of the Laplace transform for large s. So the above result hold generally and are known as the tauberian and abelian theorem. So the theorem says that suppose we have the Laplace transform fs of a function f exists, and addition ft and its derivative exists as t approaches 0 from positive, then the limit as s getting bigger of Fourier transform of ft is 0, the limit of s infinity, all those things, equal to fn 0, and if we suppose ft is bounded for all t positive, and the limit here, this is the limit, typing error there. So there's a limit t goes to infinity, ft is equal to f infinity exists. Then the limit s approaches 0 from positive, s of s is equal to that. So that's the the tauberian. Okay, let's consider example. Just this example. If you consider our ft is that function where t is positive, where a is positive, so definitely you can see ft goes to infinity. That's approaching 0. Then our function is only 1, and for the Laplace transform of ft is given by that. Okay, you can verify this thing using the definition of Laplace transform. And then if you take a limit, you can apply the second and third definition here, that and that. Okay, so that give you number there, the second line there, and as well as the third line. All right, so what we can see, the tauberian and abelian theorem is that will make the calculation much simpler. Yeah, to find the when s is getting big. And then we go to the Watson lemma. So the use of Laplace transform leads to integral of the form. So this is the Laplace transform of the function fx given by that. So one is often interested in trying to estimate this integral for s large. Yeah, the point here is for s large. Yeah, so this is where Watson lemma becomes extremely useful. Observe that for well-behaved function ft, the dominant value of the integral here will occur in the vicinity of t0. Yeah, so this suggests that we would be able to estimate the integral by replacing the ft by its local expansion for t equal to 0. So that's another point there you need to watch. So the more formal result is summarized in Watson lemma. So in this part here, and consequently, I just read from the notes there, and when necessary, I just write. Okay. So for the I think for this part, I just read whatever written in your notes. So the Watson lemma, suppose ft is of that form, yeah, of order e to the at, right? St goes to infinity, and in some neighborhood of t0, ft can be expanded as that. Okay, so we have that terms and as well the error terms there, where rt is bounded. Then the Laplace transform of ft has the asymptotic expansion. Yeah, has asymptotic expansion f as that. So this is the Laplace transform of ft when s is big enough. Yeah, when s big enough. So that's the form we have. So that's the proof. So what I can say from the proof, you just follow this proof. It's not difficult to understand. Yeah. So we split the limit from 0 to infinity into 0 to tau to infinity, means the small part and the bigger parts. And then we just substitute what ft is. Ft is given as summation of those series there, and we have Rn, and this part is here. And then we analyze each of these terms. Yeah, analyze each of these terms. So you can see from here, this part here. All right, this comes from the first part here. You just factor out the sum of ak, put it outside, and then the rest you can get e minus st t to alpha k. So you have those things. Okay, and then you rearrange those things, then you can evaluate. So this this the gamma function is defined by that. Yeah, the gamma function is defined by that, so you can easily see those things. You just integration by parts couple of times, then you can have those. And then for the second terms there, all right, so we use the properties of R, which is bounded. Yeah, R is bounded, so that less than something, all right, is given by just substitute what R is, and then you can have the solution is of order 1 over S alpha plus n plus 1. And finally the final terms here, final terms, you can have those things, and then when you combine everything here, so that give you the result of the Watson lemma. Okay, so Watson lemma is extremely useful, powerful, and can be used to generate asymptotic expansion from the knowledge of the local behavior of the integrand in Laplace type integral. So if you look at this, next look at this example. So let's consider this example in more detail. We consider the parabolic cylinder function d nu z, where we define d nu z as e minus z squared over 4 over tau minus nu, integrate from 0 to infinity e minus zt e minus t squared over 2 dt over t nu plus 1, which is valid for real of nu negative. So we apply the Watson lemma to the function ft. So what we have, our ft can be written as, so this is from the that part, this is our ft, right? So the ft is e minus t squared over 2 t minus nu minus 1, and this you can write that as a summation of minus 1 to n, n from 0 to infinity t 2n minus nu minus 1 over 2n over 2 factorial. Okay, so we use the Watson lemma. So Watson lemma, that we can find the asymptotic behavior, asymptotic expansion when s getting bigger, right? So we can have, using Watson lemma, so we can have d nu of z. This is e minus z squared over 4 over tau minus nu. So this is the front part there. For the integral here, because we use the Watson lemma, so that will give you summation n from 0 to infinity, that minus 1 to n tau 2n minus 1 minus nu over 2n n factorial z 2n minus nu. Also, the result is valid for real of nu is I think this should be positive. Okay. So the Laplace transform is very useful for solving a number of ODE problem, PDE problem, and other problem as well. So let's see some of those examples. Let's say, example, let's suppose that we have f n is given as that integrate 0 to infinity e minus nx fx dx for any n integer, and if s is summation of n equal to 0 to infinity fn, this is summation of n 0 to infinity, 0 to infinity, we have fx e minus nx dx. Okay, that's the definition of the Laplace transform. And assuming that we can interchange the summation and integration, yeah, just interchange the summation and integration. So what we find that s is integrate 0 to infinity, so we have fx and some function hx dx, yeah, where your hx is actually summation of e and x, yeah, and then you can the summation of e minus nx for n 0 to infinity, and this is just 1 over 1 minus e minus x, yeah. And then so it's not difficult to follow from you, not need a step-by-step process. And then if you consider let a positive and p positive, and the function fx, let's say function fx is given as x p minus 1 e minus ax over tau of p, so that with this fx, if we substitute into our function, so what we have fn is given as integrate 0 to infinity e minus n x e minus nx. You just substitute this function f into your given function f earlier. This is x p minus 1 e minus ax over tau of p dx, and then of course that part you can factor out. It's free of variable x, you can take it out. So what left is so we have 1 over tau of p integrate 0 to infinity x p minus 1 e minus n plus a x dx, and this is just 1 over n plus a to the p, and hence we have our s is actually summation of 1 over n plus a p, n from 0 to infinity. So that gives us integrate 0 to infinity 1 over tau p x p minus 1 e ax over 1 minus e minus x dx. Okay, so if we take a equal to 1, so we see that the integral 0 to infinity x p minus 1 e minus x over 1 minus e minus x dx, this is the gamma function, rho p, and zeta function. That's a zeta function. Zeta function. Yeah, zeta function defined as the zeta function we define as, so zeta of p, this we define as 1 over n to p, n from 1 to infinity. Okay, and we have another short example that you can read by yourself on that involve a zeta function. Okay, so I think I'll stop here for this video. So what we have done here is that we work on tauberian and abelian theorem, where we have couple of properties that allow us to evaluate and as well as Watson lemma, that allow us to generate the asymptotic expansion and hence to evaluate the what we call this Fourier Laplace transform for S big. Yeah. So I'll stop here, and for the next video I'll go to the Mellin transform. So for this thus far I have completed the Fourier transform and Laplace transform. Of course, in the literature you can find many other applications as well as many other basic properties that are not covered in these notes. Right. So for now, thank you.